Yeah.
Luciano. All right. So while Eliu is getting set up, Eliu Huerta from Argonne National Lab will talk about kind of the other side of this with all of the things that nature may offer up, and Luciano already showed you parameter spaces. How on earth do we take advantage of all of that and use that information when we try to work on the experimental side to look at the experimental data, which is largely a lot of noise, and try to extract out the data from, or the signals from that data?
Okay. All right, so yeah, let's try to connect the present with the future. And I'm going to start with AI for science. And the context is related to all the dreams that we had about having observatories, telescopes, etc., that would allow us to study the universe with incredible precision. And well, we are at that point. We now have the LIGO observatories, Virgo in Europe, Kagura in Japan, the Legacy Survey for Space and Time. So there you have the data. Now the question is, how are you going to extract knowledge from these massive data sets? And the thing is, it is not just about using exascale computing to do this, because everybody is thinking the same way. And just having exascale computers will not solve these problems. There are many different science missions that require supercomputing. So the approach that we can try to use is to change the signal processing tools that we are using and then maximize them with exascale computing in a way to boost human intelligence with these powerful machines. Now the challenge is that innovation is not easy. People tend to do things for decades, and then when they are challenged with new ways of solving problems, they are reluctant to change, right? And the other thing is sociological factors. As physicists, we think that there is a way to explain everything with equations. And we don't want data to tell us what it is in there. We want to tell data what it is. And that's sometimes a bit arrogant. And the other is long-term programs. Sometimes when something seems to be working, we just want to continue funding those lines of research, even though sometimes they are not up to the challenge. And so here is where it is important to have critical thinking, figure out whether new ideas are worth pursuing, and then if you believe that you have a good idea, then you have to have some resilience. And have in mind that to do discoveries, you do not need a paradigm. You only need good ideas. And so let's talk about some of these. And this is going to be related to what we have been talking about, black hole collisions. So here you see a visualization taken from a numerical relativity simulation from the Einstein toolkit. And here the challenge is that when you are trying to detect gravitational waves, well, the data is lightweight, but it is high dimensional, and it is fast. And so the question is, how can you characterize these sources quickly when you have to scan this parameter space? In 2017, when LIGO announced the discovery of the first neutron-star collision, we worked with LIGO scientists to connect the Blue Water supercomputer that was housed at NCSA, and then we connected that to the LIGO data grid, to the Open Science grid. We used containers and all of that, just to demonstrate that that signal was in the data. Even though we were using Blue Waters, which was a petascale supercomputer, we had to use that machine for days just to process, a little bit of data. So the question is, are we doing this right? Or do we need to change the way we are solving this problem? Because that was just one signal. Now, if you look at this zoo of different black holes and neutron-star collisions that LIGO and Virgo have detected in the last few years, then this is telling you you need to change the way you're doing discovery. And so what we proposed was to not be in the driving seat, but now to try to learn from data. And here the name of the game is that you want to couple deep learning with GPU-accelerated computing. And the different approach, not from a physicist, but from a data scientist is, what can I learn from data? I don't want to go and characterize noise. It is non-Gaussian, not stationary, very complex. I don't want to create a model to understand noise. I want the neural net to understand the statistics of the noise. and then what happens when one signal, a model signal produced by one of these numerical relativity codes, is contaminated by noise. And so we did that, and we broke down the challenge in several pieces. Let's start with a prototype. Let's just consider black holes that are not spinning. Let's create a neural net, let's train it, and let's see what happens. And so by the end of 2016, we put a paper out in arXiv where we described how to create a neural network, a very shallow neural network, really simple, but that it was able to process simulated data faster than real time. And you could find gravitational waves with a false positive rate of 1 mistake for every 200 seconds of data. Yeah, it's a prototype. But what we learned here is that instead of using a large bank of model signals to find gravitational waves through template matching, now you can do hierarchical learning. So you train the neural network, and then you forget about the template bank. It's no longer needed. You don't have to go and match the data with every single model waveform in your bank. All that information is encoded in the net, and that is why you can process data really fast. So it was positive. But a comment we got from the community was, yes, this is simulated noise. Try this with real LIGO noise, because it is very complicated. So 6 months later, we demonstrated that it was, again, possible. Again, same considerations. This is a two-dimensional signal manifold, use the masses of the black holes, but we were able to process data super fast. There were a couple of things to be done. Number one, we need to increase the dimensionality of the parameter space. And we need to work on reducing the number of false positives. So this entails going from just 2 dimensions to 4 dimensions, so that you consider the spin of the sources. And that is a major difference, because now you go from using 40,000 model signals to over 30 million model signals. And at the beginning, we were only using a handful of GPUs with Tom Gibbs' help. But now, if we continue doing that, we will need a month of computing. So we had to do something different. And the difference was to go and learn how to distribute the training. And we started at NCSA with only 64 GPUs. But again, it was taking a lot of time. But with the baby steps that we took at NCSA, then we moved to Summit. And we used over 6,000 GPUs to reduce the training time to only an hour and a half. Now, let me just give you some context here. When you are distributing the training, basically you are computing gradients, and then you need to combine them. That's a very noisy process. And so when you accelerate the training, you are also doing a very messy process. And so just using many GPUs does not mean that you will get an optimal neural net. So we had to deploy new optimizers in Summit. But it did work. And the other thing that you see here, again for context, in 2017, when we put the first few papers out on neural nets, it was incredible to use 1,000 GPUs to train, I don't know, ResNet 50. People were competing for the Nobel Prize just doing that. A couple of years later, using 6,000 GPUs is like, eh. So the field is moving super fast. And here, the beauty of this is that when you can do things at a scale, now you can incorporate the physics of the problem in the design of the architecture, the loss functions, etc. So later on, with all this knowledge, we decided to go and create an ensemble of models and then process real LIGO data. And here, the name of the game is that when you have an ensemble, it's as if you were watching something with a few friends. So there is a car crash, and when all the friends agree that that person is guilty, then all of them are, in good accord. But if someone says, no, that other person was the culprit, then we cannot make a decision. And so by using these ensembles, we get more certainty when we detect a gravitational wave. So this was a really good approach, and we decided to push it a bit more. So we went back to Summit, created 4 models, and now we were able to share them with some colleagues at the University of Chicago. They placed the models in a model hub. They connected that model hub to a supercomputer at NCSA, and with PhoneCakes, or what we now call Globus Compute, they process LIGO data faster than real time without knowing the physics of the problem, just following code that was reproducible. And what they found is that they could process 1 month of real LIGO data in just 7 minutes. They found all the different signals that were in that month, and there were no mistakes. So you remember we had 1 mistake for every 200 seconds of search data. Now we are making no mistakes in 1 month of data. So very good and reproducible. We released the models, obviously, because we want people to verify that what we say is for real. And so here you see we have a card that tells you when the model is fair, and fair means it is findable, accessible, interoperable, and reusable. And it is always being built again, different versions of Python. And you can see here how many people have verified the statement that we made. So it is incredible. And this got some press, and we got a paper in a good journal, etc. And the importance here is that people are using these tools, right? This is not just hype. We are producing tools that the community can use, and they have been used extensively in Kaggle challenges, machine learning competitions that we have organized with colleagues here in Germany, etc. Now, since we were doing this, we decided to automate the process, right? When people want to use AI, they want to go and automate things. So we created a workflow to produce models at the scale in Summit. Then we identified the best performers, and then we can quantize them with NVIDIA TensorRT, and then we deployed the entire ensemble in the Theta GPU supercomputer at Argonne. And here it was necessary to do some tweaks because TensorRT is off the shelf, good to run on a GPU. But we deployed this over the entire Theta GPU supercomputer, and we found that we could process data over 50,000 times faster than real time. And so we produced 5 years of synthetic LIGO noise, and this is very easy to do. So consider that you have 1 day of data, and now you're going to shift the data with respect to each of the detectors by 1 second. And then you do that many times. So you can create new data sets because now the data is out of phase, and you can figure out whether the model is identifying a real signal or a fake signal. And so when we did this analysis, we found that on average, the ensemble was making a mistake for every month of data. So it is really good progress. That is black hole detection. So here it is important to do things in real time or faster than real time. But for neutron stars, what Luciano was talking about, you don't want to just detect in real time. You want to forecast the future. You want to have a model that senses when a signal is in the data. And the reason for that is that when these neutron stars are very close to each other, they not only emit gravitational waves, they also emit electromagnetic radiation. And so you want to see the flash in the sky and then point telescopes to pinpoint where these events are taking place. And so we introduced a new idea in gravitational wave astrophysics, the idea of forecasting, like what economists do. And I hope they are doing a good job in the US. But anyways, what we found is that for real LIGO data, and this is the first neutron star detection, we could see, or we could sense the presence of this signal up to 10 seconds before they actually collided, even though there was a massive glitch or noise anomaly in the data. If you again remove the glitch, and here you see that the neural net is not even aware that there is some contamination in the data. This is remarkable. And so this is great for astronomers because you can be processing the data, and then you say, well, in 10 seconds, there is going to be a neutron star collision over there. And so astronomers can go and pinpoint the telescopes in that direction. And now for model signals like neutron star and black hole collisions, we play the same game. And then you see that even 30 seconds ahead of time, you can predict that one of these objects is going to happen in the universe. Very nice. And when you go and consider more exotic signals like eccentric mergers, where you have elliptical orbits and now the signals are very complex, you can again play the same game. So with several seconds ahead of time, you can predict that these events will take place, and you can even predict the area in the sky where this event can be localized. Okay. Now, I'm going to change the topic because we have been talking about numerical relativity, and we have said that it is necessary to use supercomputers to understand the final part of the signal, if you want the merger and ring down. This part can be well described with analytical relativity. But to solve this final part, we need supercomputers. Well, we asked the question, can neural networks learn the physics that is encoded in these last few cycles? And the answer is yes. If you create signals and you feed this information into neural nets, they can speed out this final part of the gravitational wave signal in milliseconds. So you no longer need a supercomputer. What is even better about this is a transformer model, which is very popular. Let me interpret this figure for you. This is an attention head. So it is a component of the neural net. It is something that the neural net is paying close attention to. And so this is the signal that you feed into the neural net, and this is what it is going to spit out. So what you learn here is that the first point that is produced by the neural net is strongly correlated, because you see red here, with the last few points here. That makes sense, right? For continuity. Now, the merger and ring down, you can see here that is strongly dependent on the initial part here, but also on the final part. And that's what we know about black hole physics. The total mass of the system determines the length of the signal, and that's very important at the beginning of the signal. And you can see that this part depends very strongly on this. But as well, you can see that this part is very dependent on the physics happening here. And that makes sense, because there is where the spins of the two objects are at play in the dynamics of the gravitational wave. So it is telling you that the merger and ring down, the evolution that you see here, depend very strongly on the total mass and the spins of the two black holes. And this is black hole physics. Even the table is having some trouble with black holes. Anyways, so that was the evolution of these gravitational waves. Now, let's see whether we can use AI to accelerate the modeling of these complex equations. And we started this because in the modeling of neutron stars, there is a lot of turbulence. And there are some PDEs that are very complex to solve. And so we started looking at these 2D magnetohydrodynamics simulations with the intent of capturing the physics that you see in turbulence. So it was a first attempt, and we showed that neural nets were able to outperform large eddy simulations, which are the state of the art for this type of simulations. And then, inspired by this, we asked the question, can we use neural operators to solve more complex equations, like tsunami modeling or coastal dynamics, for which we use the Einstein toolkit? So you need that framework to solve these equations, but with neural operators, you can solve them in milliseconds. And you can have a very accurate prediction of these quantities. As you can see here, this is what you feed into the neural operator, and then there is the prediction, and then this is the error. The prediction of the actual simulation, this is the prediction of the neural operator, and then the error. So you can see that we can reproduce very well the dynamics of this type of simulations. And here again, you have the height of the wave when it is propagating. So they are very accurate. But you could say, well, those are only 2D nonlinear couple equations. Can you do something more difficult with your neural operators? Well, recently, we demonstrated that we can solve the 2D magnetohydrodynamics equations with these neural operators. This is the first time this is done, and the paper will appear in Machine Learning, Science and Technology at some point this month. But the point that we want to emphasize here is that even though these equations are very complex and you need to use a lot of physics-informed losses to optimize them, it doesn't matter what initial condition you select. You just throw in that initial information, and you get the solution of the system for the time that you consider. It is impressive, the things that you can do with these physics-inspired AI surrogates. And the vision that we have for the future is that as we are creating these models, we release them to the science community so that they can optimize them for analysis at the edge. They can use TensorRT. And then you have the models here in the science loop. And then when you see that the models are not performing well, then you can do some reinforcement learning or transfer learning, online learning, whatever you like to do, and you continue in science mode. And only when the models are performing badly, then you go back to the HPC platform to do a retraining round. And this is the way you can really maximize the use of exascale computing and other resources. And if you're really interested in what is happening in the gravitational wave community, this is a nice, it's like a GitHub page created by students at Hanover, the Albert Einstein Institute at Hanover, where they have been following what the community has been doing over the last few years. It is really comprehensive. And I'm going to finish there. Thank you.